What is end-to-end delay? Well, end-to-end delay is the total amount of time that it takes for your data to go from the source all the way to the destination. And this end-to-end delay is going to be extremely unpredictable, extremely variable. Why is that? Because there's a lot of components that come into play. You have propagation delays, you have processing delays, you have queuing delays from the source to the destination. Now, propagation delay is pretty much fixed because when we're looking at propagation delay, we are really talking about the connectivity we have between the two devices. For example, this Ethernet wire. On each end, we have, let's say, a router connected. But in between, is there really anything in between that's going to change the propagation of those bits from one interface to another interface? No, the wire is pretty much fixed for us. So propagation delay being fixed, but processing delay, queuing delays, very, very unpredictable. When we examine the processing delay, we are referring to the time that it takes for the router to take the packet that arrived on an inbound interface, examine it, process it, make a decision, and then put it in the appropriate output queue on the exit interface. So the processing delay could be a result of many different factors. One of the factors being that our router is no longer it's no longer utilizing Cisco Express forwarding efficiently. It's no longer utilizing the fib and the adjacency tables. It is using what? It's using the processor to make its decision, for example, because maybe somebody turned on a debug or we have an issue right now in our environment and our router is just not working as it should be. So the processing delays could be due to many different reasons, even access control lists or certain features that we've enabled on the device that is making the router use a lot more processing CPU power than relying on the efficient forwarding through hardware using Cisco Express forwarding. The queuing delay is the time that our packet's going to hang out in the output queue. So it's the waiting room. You're waiting for what? You're waiting to be put on the wire. Now, why might you be waiting in the queue for a very long time? Because there's other packets in there that are taking up space. And they are large packets and they are slowly being serialized, meaning placed into bits on the wire. So all of these come into play. And all of these can be variable depending on the amount of traffic, the resources that are being used on that particular router or the resources being used on the network. And we have that propagation delay, which is the time it takes to transmit that particular packet. So from one interface on one device to the other, which is typically going to be constant. So the big deals here are processing delay, queuing delay, and serialization delay. However, we live in a day and age where our routers and our switches and our network links are much, much faster than they used to be. We're dealing today with 10 gig, 40 gig, 100 gig links, where back in the day we were dealing with Ethernet and fast Ethernet. And when TCP was invented, TCP had a window size field set to a maximum of 65,535 bytes. So the window size says, this is how many bytes I can send before I need an acknowledgement so I can send more. Well, in a 10 gig environment or a 40 gig environment, could I theoretically have larger window sizes? Could I send a lot more data? I could. But I'm stuck at the 65,535 barrier of that TCP window size that was created way back in the day. Not only that, our networks are much more reliable than they have ever been. So with that reliability in place and the fact that we have large buffers on routers, we have higher speed bandwidth, better processing power on our devices, that's kind of a point that slows us down now, that window size, where we could transmit a lot more data more often now. We're being held back. So to improve upon that, we have the TCP window scale option. It allows us to have larger window sizes. So the window size maxes out at 65,535 in the TCP header. But this extension, this addition to the header, so they haven't changed the header, we've just given ourselves the ability with this window scaling option to send more. So if everything's going really, really well, we could break through this barrier of 65,535 and send more. We can send a lot more data at any given time before it has to be acknowledged by the receiver when we're using our TCP sessions. So for example, you might have 10 gig links in your network and they're being underutilized simply because of the behavior of TCP with this maximum window size. But the window scaling option now with TCP gives us the ability to take advantage of these high-speed links, send a lot more before they have to be acknowledged. So one of the ways we can determine what is the best window size to use, for example, would be this formula you see here, the bandwidth in bits per second times the end-to-end delay. So if you have your bandwidth in bits per second, you multiply it by your end-to-end delay. Let's say it is 0.08 seconds. 0.08 seconds. And your bandwidth is even a gig link. Well, what is that going to give you? It's going to give you a total of 800,000 bits per second. So your bandwidth times your end-to-end delay. So 800,000 bits per second. So what's that going to equal? Well, divide that 800,000 divided by 8, and it's going to give you your bytes. So 100,000 bytes. So theoretically, my window size could be 100,000. I could send 100,000 bytes before I need an acknowledgement, which is going to make our communication from end to end across our network much more efficient when we're utilizing TCP.